Hello and welcome back. I just want to spend a few minutes explaining some of the concepts that we learned about curves on the plane, but now surfaces in 3D. So it's going to be a much shorter video than the previous one, and we're going to be discussing surfaces instead of curves. Just a couple of concepts. Surfaces are really beautiful, and we could spend years, some people spend all their life studying surfaces. But once again, we only have time for a few key concepts that will help us to understand, for example, active surfaces, how to do segmentation of volumes in three-dimensional images. Again, just a few concepts. We have a surface. On a surface, basically, we're only going to be talking about surfaces in 3 dimensions. And basically, on a surface, we can draw curves. Here we have curves. Now, basically, each one of these curves is in 3D now. So you have to have X, Y, and Z. But we basically have the surface. Imagine that the surface is basically floating on a plane. So the way we parameterize the surface is now with two parameters, U and V. Remember, for curves, we have only one, P. For surfaces, we have two. So we basically are on the plane. So we have U and V on the plane. For each U and each V, we have an X coordinate, Y coordinate, and Z coordinate. And that's how we represent a surface. 2 parameters, 3 coordinates. In curves, we had 1 parameters, 2 coordinates because we were on the plane. We can have curves in 3D. There will be 1 parameter, 3 coordinates. For example, this one. So that's a surface. Now let's define normal, area, and things like that on the surface. But if we have curves, we can take derivatives as we were doing on the plane. So we can take a derivative according to the U parameter and according to the V parameter. So we can basically be on a curve and basically say, let's just take a derivative of that curve according to U and according to V. If we do the cross product of these two vectors, we get a third vector perpendicular to these two. Once again, basic algebra. So the normal is the cross product of the two. So the derivative of S according to U is tangent. The derivative of S according to V is tangent. They will define a plane which is tangent to the surface at this point. If we do the cross product between them, we get a normal to the surface. And again, we are going to normalize that because we're interested in unit length normals. So we have derivatives, which means tangents, and then the normal. If we have derivatives, we can, for example, define the element of area. We know that once we have two vectors, the determinant of the matrix composed by those vectors basically defines the area of the parallelogram that we see here. So if that's infinitesimal, we have elements of area. If that's integrated across long regions, then we have the total area. So same type of concepts. We have length on the plane, we have areas here. We also have length because the surface is just a lot of curves. Nothing else than that, nicely organized. So once again, here is the parameterization and here is the normal. Let's see the example of something that you are familiar with, which is basically graphs. The same way that we saw graphs on the plane, we can see graphs in 3-dimensional space. So we have a coordinate system, X, Y, and Z, and basically we define a graph that is, again, floating on space. So our parameterization is X equal to U. Basically, X is one of the parameters, Y equal to V, and then Z, basically the height of the surface, or in this case, the graph, or the function, is just a function of these two. A particular case. Think about an image, for example. An image is a particular surface, is a function. So the plane of the image is X and Y, or U and V. The gray values of the image is the height, means Z. So you can think about images as surfaces, in particular case as functions or graphs. And that's a very interesting interpretation. We can basically compute things. We can compute the normal of an image. As we saw in the previous slide, basically we treat the image as a surface, we take derivatives, we compute the normal of an image. So we bring a lot of concepts of differential geometry into image processing. Now, what about curvatures? So the basic idea is very simple. Once again, we have curves. If you have a curve, you can take first derivative according to arc length. This is a curve in 3D, but it's the same concept. And second derivative. Second derivative will basically give you the curvature of that particular curve that you took. For example, this one. Now, sometimes you want to project that curvature. Remember, first derivative is tangent. Second derivative is perpendicular to the curve, not necessarily to the plane. You have a curve, there's a lot of things that can be perpendicular to that. So you can take it and project it to the normal or the perpendicular to the plane if you wish. And that's basically sometimes called the normal curvature. So you take a curve, you take second derivative, that gives you a vector, and you project that vector into the perpendicular to the surface. But that's about, basically, maybe you're thinking about a curve. But if I have a point, let me just mark that here. If I have a point on the surface, there are multiple curves on the surface that go through that point. So look at all the curves. There are multiple of them. So what exactly defines the curvature at that point? It turns out that there is one of these curves that when we treat it as a curve and we compute the curvature is the smallest possible. And there is another curve that is the largest possible. So we basically define the principal curvatures of a surface in the following way. You're in a point and you basically try all the possible curves on the surface that go around that point. And you basically compute the curvature. Now we're talking about curves. This curve has a curvature. This curve has a curvature. You compute all of them. There's one which is the minimal and one which is the maximal. Sometimes there's more than one. For example, a sphere might basically have more than one. All directions are the same. But you have, for regular surfaces, you have at least one which is the max and the other which is the min. And those are called the principal curvatures of the surface. I'm going to just tell you a bit of extra information. The curve that gives you the max and the curve that gives you the min are perpendicular to each other. Now, and there are ways of computing this. You don't have to really try all the curves. There are ways of computing. I'm just talking about the concepts here. So there's one direction which is max, the other is min. Think about a cylinder. When you cut a cylinder perpendicular to its axis, there is one direction that you basically get a circle. What's the curvature there? 1 over the radius. We know that. There's another direction, in the direction of the cylinder, that you get a straight line. What's the curvature there? We know, it's 0. So in one direction we get 1 over the radius. That's a maximum. The other you get 0. That's a very nice thing. It's a surface that in one of the directions the curvature is actually 0. So on a curve, there's only one curvature. You're turning, and there's only one direction to go on the curve. On the surface, you can go in multiple directions. And then we pick one, which is the maximal direction that we curve the most. One is the minimal, where we curve the least. And actually, that basically completes what's called the mean curvature, which is the average of both of them, and the Gaussian curvature, which is the product of them. So what's the Gaussian curvature of a cylinder? 0. At every point in one direction, basically it's a straight line, so it's 0. And there is a lot of beautiful differential geometry on surfaces, a lot of it due to Gauss. Really beautiful. But these are the basic concepts. So you have the same as on the plane, the curving of the surface, but we have curving in multiple directions. We have the max, the mean, and normally people say, instead of taking the max and the mean, let's take the average and the product. From this, you can, of course, from the average and the product, of course, you can go back to the max and mean, or vice versa. So these are basic concepts of surface differential geometry. Again, we have normals, curvatures, the same kind of concepts that we had for planar curves. So now, after these two videos, one relatively longer than the other, you're an expert in differential geometry. And at least you have the tools to understand what's coming next, which is deformation of curves, meaning deformation of shapes, and the relationship of that with active contours, active surfaces, and even with image denoising and image enhancement, as we're going to see. Remember, images are surfaces, so we can treat them with the tools that we just learned. They have curvatures, they have normals, they have the same concepts of differential geometry. I see you in the next video. This is getting really, really exciting. I hope you're having fun. See you very soon. Thank you.